So the focus of the previous video was showing us how conservation of angular momentum as an idea is very similar to conservation of linear momentum. The focus of this video is going to be showing us that how we work conservation of angular momentum problems is also very similar to how we work conservation of linear momentum problems. And in particular, it's similar to how we work one-dimensional conservation of linear momentum problems, because we're going to deal with angular momentum that always lies along the rotational axis for some system. So because our angular momentum is going to lie along a single axis, it's going to act just like a one-dimensional conservation of linear momentum problem. So let's look at a conservation of linear momentum problem first, just to remind ourselves how this works. So let's say I've got two blocks. Block 2 is initially sitting at rest on a frictionless surface. Block 1 slides to the right. It has an initial speed. It hits block 2. They stick together and slide off to the right as a single entity after the collision. Well, let me start by drawing the initial and final states of my system. So again, initially, block 2 is just sitting there. Block 1 is sliding into it. At the end, now they're stuck together and moving to the right with a single final speed. Well, of course, I want to make sure that I can work this as a conservation of momentum problem. And so for momentum to be conserved, that means that the net external impulse exerted on the system needs to be zero. And so that this happens in one of two ways. Either the net external force acting on the system is zero, or the time at which we let that force act is negligibly small, and so therefore the impulse will be zero, because that force, even if it's there, doesn't really have a time to act on our system. So when I think about the external forces, well, I know gravity is going to pull down on both blocks. There'll be a normal from the surface that will cancel out that gravitational force. There's no friction here because my surface is frictionless. And so sure enough, in terms of external forces, they all cancel out. Now, even if we said that this surface had friction, because the collision happened so fast, delta t is small enough, it's effectively zero because of how quickly the collision occurs, so that even if there was friction on this surface, this collision would happen before the blocks had really had a chance to move, and so friction wouldn't have a chance to act on the system during that circumstance either. So sure enough, linear momentum is conserved, which means I can work this as a conservation of linear momentum problem. Well, to do that, I want to start by drawing some linear momentum vectors. So I'm going to draw the two initial linear momentum vectors, one for each piece of my system. So block 2 is just sitting there. Its initial linear momentum is 0. Block 1 is moving to the right, so its initial linear momentum points to the right. Afterwards, basically I have a single object, because now blocks 1 and 2 are stuck together, and so I've got a single linear momentum vector that points off to the right. Vector problem, I need a coordinate system so I can break those vectors up into components. So I'll just let the x-axis lie along the direction that both these momentum vectors point. And so now I can go ahead and start working my conservation of linear momentum problem. So I know momentum is going to be conserved. I have my two vector diagrams showing me all of the initial momentum vectors and the final momentum vector. What I need to do at this point is just break them up into components. I can use a table, but because this is a one-dimensional vector problem, really this is just about making sure that we get the right signs and knowing what to plug in for magnitudes. Both my non-zero momentum vectors point in the positive direction. The magnitude of the initial momentum of block 1 is going to be mass 1 times block 1's initial speed. The magnitude of the total linear momentum of the system afterwards is m1 plus m2, so the total mass of that combined block times its final speed. And so I can set up my x component equation. P1 initial plus 0 equals P12 final. Plug in my substitutions for magnitudes, and again I've got a single equation. One equation means one unknown in terms of going through and solving for whatever I'm asked to solve for. So this was our process for solving a one-dimension conservation of linear momentum problem. Well, if we look at a conservation of angular momentum problem, what we're going to see is it's a very similar process. So let's look at an example where we've got a rod, we're told the length of the rod, we're told its mass. the rod can rotate about a pivot at one end, and it's initially hanging straight down. We've got a particle that's traveling with an initial speed and flies horizontally into the rod. Those two objects stick together, and then that system starts rotating counterclockwise about the pivot after the collision. So again, I'm going to start by drawing in initially what's my system look like, at the end what's my system look like. So here I've got the particle as it's flying in to the bottom end of the rod. The rod is hanging straight down, can rotate about the pivot point at this end. At the end, we've still got the pivot point up here. Now the particle is stuck to the rod, and the two of them as a system start rotating counterclockwise about this pivot point. Just like with our linear momentum problem, we want to make sure that we can actually work our conservation of angular momentum here. So we need to check, is the net external angular impulse acting on the system 0? Well, again, that happens for one of two reasons. Either the net external torque is 0, or the time that that torque has to act is negligibly small. What forces are there that could cause a net external torque? Well, gravity obviously acts on the system, but because the rod hangs straight down, gravity doesn't exert a torque about this pivot point on the rod. It points straight down. As the particle basically slams into the rod, so just before the collision starts, there's very little torque that gravity generates on the particle about that pivot point as well. We could envision where the pivot has friction, but of course that friction is going to act at the pivot point. So the normal from any friction generated at the pivot, neither of those forces would generate torques about that pivot point. So this looks like a situation where, sure enough, the net external torque is effectively 0. Even if it wasn't, of course, the collision happens over a really short amount of time. So even if there was some net external torque, we're not giving it any time to act on the system because the collision happens quickly, which means that the angular momentum of our system is going to be conserved. So I'm going to start in the same place I did with my linear momentum problem that says I need to draw out some angular momentum vectors. I'll have two of them initially because, again, I've got two pieces of my system. The rod's easy. It's not moving at all, so it has 0 initial angular momentum. The particle, well, I need to treat it like a particle, which means there's a right-hand rule that helps me figure out the direction of its angular momentum. And so for my particle, I'm going to point my thumb in the direction of r, the position vector. I need to hold my right hand so that my fingers are pointing in the direction of the linear momentum, which means in the direction of the velocity. So in this case, my thumb points down, the fingers of my right hand point to the right, and when I do that, my palm is pointing back up out of the screen. So I have an initial angular momentum for the particle that points out of the screen. After they stick together and start rotating, well, again, I have a right-hand rule that says curl the fingers of your right hand in the direction your object is rotating about its pivot. And in this case, because they're rotating counterclockwise, when I curl the fingers of my right hand counterclockwise, my thumb points back up out of the page. The angular momentum vector I need to draw for the system in the final state also points up out of the page. It's a vector addition problem. I need to pick my coordinate system. So I'm going to let positive z point out. I know that I have conservation of angular momentum. I've drawn in the angular momentum vectors that I need to add together. I've picked the coordinate system to do that. And so I can set up my table just like we did before. Again, it's one-dimensional, so mostly this is about making sure that my signs are correct and then thinking about the appropriate things to plug in for magnitude. So my two non-zero angular momentum vectors are both positive. The angular momentum vector for my particle, well, I know I can calculate the angular momentum for a particle by it's the mass of the particle times the speed the particle is moving times the perpendicular distance from the pivot to the line of motion of the particle. And in this case, that happens to be the full length of the rod. So m1 v1 initial times little l, the length of the rod, is the initial angular momentum for the particle. The final angular momentum for my system, where mass objects 1 and 2 are stuck together, is just the total rotational inertia. So I1 plus I2 times the final angular speed at which the system rotates. So I can set up my z component equation for conservation of angular momentum, plug in my L's, come back and substitute in for the magnitude of those angular momentum values, and at this point the only thing left to deal with are these two moment of inertia values. I1 is the moment of inertia of the mass, and so calculating the moment of inertia of a point particle, it's equal to the mass of that particle times the perpendicular distance from the pivot to the particle's location squared, and that happens to be the length of the rod. So m1 little l squared is the moment of inertia for the particle about that pivot point. The moment of inertia for the rod, well, I know when I go look up the moment of inertia for the rod rotating about its center of mass, it's 1/12 ml squared. The pivot point here isn't at the center of mass, it's at the end of the rod, and so when I use the parallel axis theorem, I get that the moment of inertia for the rod in this case, for this particular choice of pivot, is 1/3 mass of the rod times the length of the rod squared. So I'm left with one equation. One equation means I can have one unknown to be able to solve this problem.